Alright, welcome to Chapter 15 video for physics class. This one's going to be all about sound. If you remember back in Chapter 14, we learned about waves and oscillations, and so sound waves are a specific example of waves and oscillations, and this whole chapter is going to delve into sound waves, how they're produced, some of the different effects that we can observe with them, etc. So the first thing is a little overview of the topics. Sound waves, detection and perception, and Doppler Effect are in 12.1 in the book. Except this is not 12.1. For some reason I put 12. This is actually chapter 15.1, sorry. And 15.2 is music, the different sources of music, resonance, and then sound quality and distortion. Alright, so let's get started. So the first thing is, if you recall, there was two types of waves. One was transverse, one was longitudinal. Longitudinal means that the physical disturbance, the motion of the particles, is in the same direction the wave is traveling. So with a sound wave, if it's traveling through the air, say in this picture, if it's traveling through the air left to right that way, then the physical particles are going to oscillate back and forth left and right. But to draw the amplitude, we still keep the we draw it as a transverse wave just so we can visualize it, because it's kind of, you can't really draw a wave like this without having in real time seen the particles move back and forth. But you can visualize this as the amount of oscillation of the particles, even though you know they're moving forward and backward, not up and down. So a sound wave has all the normal properties of any of the other waves that we've studied, such as amplitude, speed, wavelength, frequency. And this formula here is really, really important for sound waves. The velocity of sound equals the wavelength times the frequency. Except the velocity of sound is going to be pretty much set for a given condition. So in room temperature air, the velocity of sound is 343 meters per second. But in other materials or mediums like water or steel, like if you bang on a railroad track with a hammer, the sound wave, the oscillation of those particles, will travel through the iron or the steel at a much faster velocity than it would through air. There's a question in the homework about that as well, I think. So if you want to look up the speed of sound for other scenarios, check your book, page 405. You don't need to memorize any of these, but you do need to know how to use them. Okay, so how do you detect sound? Well, the ear is really complex, and it consists of three different parts. You've got the outer ear, the middle ear, and the inner ear. And so what your ear is detecting on your eardrum is kind of like a little membrane that can oscillate. And so as sound waves hit your ear, that means that the pressure in the air is changing. It's high pressure and then low pressure, and then high pressure and then low pressure. And it's changing a couple of hundred times per second. And so your outer ear, the sound is coming in through here, through this canal. It's oscillating this membrane, and then inside you have fluid. And so as this membrane oscillates, it sends vibrations through the fluid into the inner ear, and then in your inner ear you have lots of little hairs, and they all detect different wavelengths or different frequencies. And so depending on what the sound wave is that's coming in, it will kind of I don't know, tickle or like activate some of those little hairs. They're called, what are they called? Cochlea? Or that's just the whole thing? I think that's the whole thing is the cochlea. I can't remember, but maybe if you ask Dana or Brendan, they probably know better than me about the physiology of the ear. But essentially, it oscillates those little membranes, and whichever ones oscillate are connected to nerves, which are connected to your brain, which then you perceive as sound. So what we're hearing or what we're noticing is this alternating pressure, this high and then low, high and then low, high and then low, not the actual absolute value of the pressure. So that's why when you go up into the mountains and you pop your ears, you're at a lower pressure zone, but you can still hear someone talking. Everyone sounds the same up there as they sound down here, because the sound waves coming out, they cause a variation in the pressure, but that variation, it doesn't matter what its baseline value is. So if you have a variation on atmospheric pressure at sea level, or if you have a variation, the same variation up in the mountains, it's the variation that determines what the sound is perceived as by a human. And the actual variation in the pressure is really, really, really small. So look at these numbers real quick. A sound wave has an amplitude of roughly 2,000 micropascals. Okay? But atmospheric pressure is 1 atmosphere, which is 1 times 10 to the 5th, which is 100,000 pascals. So if you compare 2,000 micropascals, let me put this into pascals. If you convert this, micro is 10 to the negative 6. That's going to be you have 1, 2, 3, 4, 5, 6, 0.002 pascals. That's the size of the oscillation of the pressure, 0.002 pascals. And you're comparing that to 100,000 pascals, which is the pressure all the time. And so that's a really, really small percentage of the pressure in your ear. So right now your ear, even if there's no sound waves, is experiencing a pressure of 100,000. And then if it goes up to 100,000, 0.002, then that's what you can hear as sound, as it oscillates up and down. But it's oscillating a super, super tiny amount. So what that's telling you is that your ear is really, really sensitive. And that's why if you have really loud sounds, they physically hurt your ears and they can bust your eardrum. If this pressure oscillation up and down gets very high, then it will really damage your eardrums. So what do we hear? How do we hear? To perceive sound, what we hear is called pitch, but the physical quantity that pitch is actually frequency. So you should, in your head, if you didn't know this already, tie these two together. Pitch and frequency are the same thing. In music class or in everyday discussions of sound waves, you might say it had a high pitch or a low pitch. But mathematically or physically or numerically, what you're talking about is the frequency of the sound wave. So the human ear, it's got a wide range that it can detect. The smallest frequencies that we can hear are around 20 hertz, so that means 20 oscillations per second, and that'd be a very low, deep rumbling sound. And then the highest we can hear is 16,000 hertz, which would be at the very, very highest, like a very high whine. You would probably hurt your head, and you would be thinking that glasses are about to shatter when you hear the very highest frequency possible. And as people age, the little hairs, the little membranes in their ear deteriorate and aren't working as well. And so the older they get, they're not able to hear higher frequency sounds. And I mean, this is just an estimate value, but it cuts off around 10,000 kilohertz for older people. And then other animals, like for example dogs, if you've seen or used a dog whistle, you blow the dog whistle and the dogs can hear it, but you don't hear anything coming out. That's because the sound wave for a dog whistle is higher than 16,000 kilohertz. And so to us, I mean, there is still an oscillation on your ear, but you don't have any membranes that detect that frequency, so no signals are getting transmitted to your brain. But for dogs, the range that they can hear is a lot higher, so they can hear it even though we can't. Okay, so pitch is frequency. The second important property of a sound wave is, of course, how loud it is. So the loudness corresponds to the amplitude. So that's what I was talking about before. The oscillation amplitude is very small compared to the actual pressure on your ear, but still, you can detect it, and it can lead to very loud sounds or very small sounds. So we can detect a very wide range of amplitudes, ranging from a very whisper to a massive sound of a jet taking off next to you. So the smallest that we can hear, which is 2 times 10 to the negative fifth pascals. That's even less than the example I gave on the previous slide. And the highest we can hear is 20 pascals. That would cause physical pain. So remember I just said the baseline was 100,000. So if you're hearing an oscillation of plus or minus 20 pascals, that's about as loud as you can go without damaging your ears. And plus or minus 2 times 10 to the negative fifth would be the smallest sound you could hear. But the range, the size difference between 2 times 10 to the negative fifth and 20 is on the order of 1,000,000 times bigger or 1,000,000 times smaller. So it's a really, really big range that we can hear. And so mathematically speaking, you might have learned about logarithms. One of the useful things about logarithms is they can take a really long range of values and compress it. So if you make a logarithmic graph or a logarithmic scale, you can express a range that's 1,000,000 in a space that you can see. So let me show you what that looks like. So the range here in micropascals, so 20 micropascals was the smallest, and 20 pascals we said was the highest that you can hear without feeling pain. So this is 20 pascals, and then you add 6 zeros because the units are micropascals. So this range, from the smallest thing you can hear, which is 20 micropascals, to what's the threshold of physical pain, 20 pascals or 20 million micropascals, this is 1,000,000 times bigger. So, million. So in order to use a log scale, what you do is you set it up so that every 20 decimals So adding 20 on the log scale plus 20 on the logarithmic scale is multiplying by 10 on the actual amplitude. So if you go up from 0 decibels to 20 decibels plus 20, then this went up times 10. So here you go times 10, here you go plus 20. Okay, why it counts by 20s, honestly, I'd have to do some math or something, but you can ask in class if you want to go through that. Why they chose to count by 20s instead of 10s or something. I'm sure we could look at that and figure it out, but for now I don't know. So you can keep going like this. Times 10 again is plus 20 again. Times 10 plus 20. So if something is, say, 60 decibels higher, it's times 10, times 10, times 10. It's actually 1,000 times more pressure on your eardrum, or more difference in pressure, I should say. So you can look at these different things. It's kind of cool to see what the different values are. So this is kind of weird because it says painful at 70, very painful at 90, and then threshold of pain at 120. That doesn't really make sense. The threshold of pain means, that's the border between pain and not pain. So you definitely have lots of pain up here. Maybe it's better to say the threshold of damage, long-term damage. I don't think that a lively street conversation is actually painful, but I suppose a lot of this is open to interpretation. So the actual pressure is not open to interpretation. You can measure that with some sensors, but the subjective impression, of course, it depends on the type of person. And these are just examples of sounds that were roughly at various different thresholds. So how much is too loud? Well, if you're plugged into your iPods, I'm sure Stuart would tell you this as well, all day, then you're receiving lots and lots of high amplitude sound waves, and that's going to end up damaging your ear. It's almost like standing next to a jackhammer, which I'm sure none of us would want to do, except if that jackhammer was producing cool sounds that we really enjoyed, suddenly it would become tolerable. But when you do shooting guns or listen to fireworks, it's often useful to put in earplugs. And how earplugs work, when you actually buy a pack of earplugs, they'll say on there the decibel reduction. So you might have a box of earplugs that says like 40 decibel reduction. So it will take something that was at 110 decibels and knock it down to, say, 70 decibels. So it'll take something, well, we don't have an example. Maybe it'll take an airplane sound at takeoff and make it just sound like heavy street traffic or lively music, something like that. So that's what they do, is they tell you how many decibels they reduce the sound wave by. Okay. All right. Next up is the Doppler effect, which is really cool. And I've got 3 different videos to show you that will help you already know this effect, but it will help refresh your memory on what it is, visually see what it looks like, and then we'll go through the equation for it. The first video is listening to a car horn. So you should observe that as it's coming towards you, you hear a higher frequency, and at the moment it passes you, it kind of transitions, and then you hear a lower frequency. So let's kind of visualize why that occurs. This is an example of an airplane flying. So these blue circles represent the sound waves, and it's emitting a sound wave. Say it's got a buzzer going off or something like that. And let me pause it here. As the plane is moving forward, the sound waves each expand in a concentric circle from the point at which they were released. So if you look, for example, at this sound wave over here, the center of this one is actually over here somewhere. But since the plane is moving, the source that's emitting these sound waves is moving sideways, the center of each wave keeps getting moved to the right. So since you keep moving them to the right, on the right-hand side or in front of the plane, they're a lot closer together, and each time on the left, you've moved a little bit, so they're getting farther away. So the effect of this is that the sound waves are much closer together in front of the plane and much farther spread apart in the back of the plane. And so if you're standing here, you're hearing more waves pass you, so you're hearing a higher frequency, and if you're standing here, you hear less waves passing you, so you hear a lower frequency. The plane's going to come again now, going even faster. This plane is now traveling at the speed of sound. So what that means is, as the wave expands, the plane is moving at the same rate the wave is expanding, so it's staying on the edge of the expanding sound wave. And each time it emits a new one, the front edge of that sound wave, they all stack up on top of each other. And so you won't actually hear the plane. If you're standing over here, you won't hear the plane until it gets to you, because all those sound waves are traveling at the same speed the plane is. So you won't hear, you'll be standing here and you won't hear anything, and then bam, all of a sudden you hear kind of all those sound waves at once, right when the plane is, say, pretty much at you. Okay, the third example is if the plane is traveling faster than the speed of light. This one's pretty cool visually. So the sound wave that it first emitted is way back here, but the plane is already out here. So it's emitting a sound wave, and it's speeding off so fast that these sound waves are not able to keep up with it. And so what happens here is, if you're standing on the ground right here, for example, let me pause it. If you're standing on the ground right here, then you've got the front of all these different waves all lined up along this angled line here, and they're all going to hit you at the same time. So that's what's called a shock wave. It's kind of a conical shape coming out behind the plane, and it happens when something has broken the sound barrier. And it's because all those sound waves are hitting you at the same time, instead of you hearing one after the other, after the other, after the other. Okay, so that's what that looks like. And the third one is just another audio visualization of a plane moving towards an...
Change the airplane velocity and the observer position.
So it's coming towards you here, and it goes away. You should hear a lower frequency, and then turn. Okay, so that's just another example of the audible sound of how the frequency is higher when it's coming towards you, and then it gets lower after it's past you and it's going away from you. Okay, so let's look at that. So I don't really need to go through this slide very much. I hope I've pretty much explained everything. The waves are closer together in front of you and farther apart behind you. So I'll just jump straight to the equation that describes that. So the frequency detected is right here. This is the detected frequency, so the person listening to it. F sub s is the frequency of the source. So that's the actual frequency that's emitted. And then this here is how much it's modified by. So velocity of the wave is the velocity of the sound wave. So if, say, example, it's an airplane flying through the air, the velocity of the wave is probably 343 meters per second. But it could be a submarine underwater, or it could be something else. So the velocity of the wave is the velocity that the wave would travel in the medium without any effects alternating it. Then v sub d is the velocity of the detector. V sub s is the velocity of the source. And you have to be careful when you're doing this, because these minus signs are relative to the orientation that you draw the picture. So you need to draw the picture with the object starting on the left, moving towards the right, and then you identify to the right as positive and to the left as negative. And I'll do an example on the next slide to show you exactly how the sign notation or convention should work. Okay, so here's the example. You're driving down the road at 30 meters per second. An ambulance comes up from behind you at 50 meters per second with its sirens on, emitting a frequency of 440 hertz. What frequency do you hear as it's behind you? What frequency do you hear after it passes you? So we're going to be right here. Oh, crap. Sorry, I need to get my pen back. Okay, we're going to be right here, and we're going 30. And this ambulance is over here, and it's going 50. And the frequency of the source is 440 hertz. And we want to find out the frequency, sorry, that's getting sloppy. The frequency detected equals question mark. And the velocity of sound, we're just assuming it's regular air, will be 343 meters per second. So the velocity that we detect equals the velocity of the source times this conversion factor, the velocity of the wave minus, let me check, the velocity of the detector is on top, and the velocity of the wave minus the velocity of the source is on the bottom. So if we plug in our numbers, the velocity of the detector equals velocity of the source is 50. Sorry, no. I've made a mistake in this formula. It's frequency here. I apologize. Frequency is what's getting shifted. And it's getting shifted because these velocities are different. I apologize. So the frequency detected is the frequency of the source, that's 440, times this conversion factor, and the speed of the wave is 343, minus the velocity of the detector, that's 30, over 343, velocity of the wave, again, minus 50. Okay, and now here's what I want you to see. So you can use common sense a lot of times to make sure you don't mess these up. You know this car is catching up to you because it's going faster than you. So you know in your head that the frequency should be higher, because when two things are coming together, the waves are closer, and so the frequency should be higher. So when you solve this out, you have to get a number bigger than 440. And so we should see, because the denominator we're subtracting more, the denominator will be smaller. So let's do this. 343. Let's just minus 313 divided by 293. So our conversion factor, oh, that's a big, I got 0.1, that can't be right. 313 divided by 293 equals, there we go, 1.068 is our conversion factor. Then we times that by 440, and we get 470. So we'll hear a higher frequency as it is coming up from behind. Now, alternately, second problem is, now we're still here going 30, but now it's here going 50. Okay. It's here going 50. And so you might think, hey, the picture looks exactly the same, right? This is kind of weird. All the numbers are the same. If I plug in all these numbers, I'm going to get the same answer out. But the problem is, now it's going away from me. And so I know that it can't be the same answer. It's got to be a lower frequency. And so this is what I said on the previous slide. You always have to draw it so that the source is on the left. That's the convention that the formula is derived with. So you need to redraw this so that the source is on the left. And if the source is on the left and it's going away from you, right, you need to draw it going this way. And then you can draw your car going this way at 30. But now, because it's going away from you, you're going to put in a negative, and you're going to the left, you're going to put in a negative. So when you plug numbers into this formula, you're going to get the frequency detected is, again, 440. And then the speed of the wave is 343. But now when you plug in the velocity of the detector is u, that's 30. You're subtracting a negative, so you're actually doing plus 30. And then over here, you're doing 343. And you're subtracting a negative 50, so you're going to get plus 50. And this, now you can see the denominator is going to be bigger than the numerator. And so you'll get out a lower frequency. And let me check this real quick. Just to verify, 343 plus 30 is 363 divided by that's 373 divided by 393. Your conversion factor is 0.949 times 440, and you get 418. 418 hertz. Okay, so you can see that once it passes you and it's going away from you, you're going to get a lower frequency. Again, make sure you know the sign convention. For this formula, the way we've derived it right here, is that the source needs to be on the left. And then your orientation from that point on depends on the problem. Are they coming together? Are they going apart? Is one going left, one going right, etc. But as long as you put the source on the left, you should be able to make sense of it. And second thing is, always just use common sense to check and make sure that the number's coming out right. If the two objects are moving apart, you should get a lower frequency. If the two objects are coming together, then you should get a higher frequency. Okay, I think that clarifies everything, I hope. Just a quick summary on this slide. What I just said, objects approaching, higher frequency, objects receding, lower frequency. So now is a good time actually to take a break. If you haven't taken one yet, we're more than halfway, just a little bit of cool stuff left. So take a quick break, pause, and then get a drink, come back, etc., etc. Once you're back, here we go. Sounds of music. This is probably something a lot of you guys hopefully are interested in, and I'm not going to be able to explain everything about how musical instruments work, and maybe you guys already know this stuff and even more than I'm going to explain, but this is kind of a brief overview of the sources of sound and how they oscillate in the instruments to create sound waves that then you hear as music. So anytime you have a sound wave, you have to set those particles of air into an oscillatory pattern. And so the only way you can do that is by have a physical object oscillate and collide with them. So in a speaker, the entire speaker cone is moving forward and backward, pushing air forward and causing it to vibrate. So each different type of instrument, the classifications of instruments are based on the different ways that they vibrate the air. So in a woodwind instrument, when you blow over the reed itself is vibrating up and down, which then causes vibrations to go through the tubes of the instrument. In a brass instrument, if you've ever played a trumpet or something like that, you can feel your lips vibrating as you blow the air through the tube. So your lips are what's vibrating here, setting the air in motion. On a string, the string itself is vibrating either because it's been plucked or because it's been strummed or because it's had a bow rubbed over it. And then for percussion, it's the membrane on the drum. So it's like a stretched leather or some kind of man-made material that they use as the membrane for the drum. And when you hit it, it's going to vibrate. And how much it vibrates, in all of these cases, the amount that they vibrate depends on how tightly they're stretched, on how long they are, on where you hit them, on how long the tubes are for the metal tube instruments, etc., etc. So there's a lot of factors that go into the actual sound, but in all cases what they have in common is there has to be something oscillating or vibrating to set the sound in motion. Okay, so resonators. So when you want to make a musical instrument, you want a certain frequency to be much louder than everything else, and that's how you can make a note, for example. So many instruments can be thought of as pipes or strings that have standing waves on them, and so the standing wave, whatever frequency that standing wave is what's going to get amplified, and that's therefore what you're going to hear. So anytime you have a standing wave, if you remember back from chapter 14, a standing wave is one where it looks like it's not traveling sideways, it looks like it's just kind of oscillating up and down. There's going to be nodes where there's no motion, and then antinodes are the places where it's oscillating back and forth. So if you have a string, for example, fixed at both ends, those have to be antinodes, and then the middle can oscillate up and down. So there's three options we're going to consider in the next 3 slides. But first we have a cool video. So this video is going to be about a resonance tube, which is basically just, I mean, it's not an actual instrument, but you could think of it as a tube in a tuba or something like that. And when you have certain frequencies, they'll oscillate the air at maximum amplitude. So it's 2 minutes, just sit back and enjoy. Well, I can talk, actually. I don't know why I'm covering my face up. So she's turned on the sound waves, and she changed the values, and she stopped when it got to maximum amplitude. You can see that on the 2 ends, which are fixed, there's no oscillation of the particles inside, and in the middle, it's max amplitude, and she said the frequency she set it at is 119 hertz. She increased the frequency and everything dropped. Did you see that? So there was no resonance at those other frequencies. She increased it higher, and now all of a sudden you get a double resonance where you get a max here and a max here, and still a node there, and a node in the middle. And you notice that the second frequency that produces some kind of sound that amplifies is exactly double the original frequency. So before you just had this much with a node at both ends. Now all the particles dropped as she increased the frequency again. Keeps going. And now it's starting to get a lot higher, which is, I said, higher pitch. It sounds higher to you. Now you have 3 oscillations. Each of these oscillations is 1/2 of the wavelength, and that's triple the original frequency. So that's with both pipe ends closed. So I'm going to zoom ahead a little bit. The next thing, I guess I didn't need to. The next thing she does is she opens one end of the pipe. And she does an oscillation with one end of the pipe open, so that you need to get an oscillation here at this end as well. depending on both the length of the pipe and whether it's open or closed at the ends, you're going to get resonance, which is the sound waves that are amplified at different frequencies. And so by choosing the length of the pipe, you can choose which frequencies will be sound amplified. Okay, so if you have a closed pipe, which to me I am actually saying is closed at one end and open at one end, an instrument that's an example of that is a clarinet. Like we just saw in the video, you need to have an antinode at one end plus, you need to have a node at one end that's closed and then an antinode at the end that's open, so these particles are oscillating. And the actual smallest wave that you can fit on there is 1/4 of a wave. As you can see, get my pen again. So the entire wavelength would be something like this. Okay, so you have a node at this end, and then you have a maximum right here. So this maximum right here is this maximum right here. So right here you have 1/4 of a wavelength. So if one end is closed, 1/4 of a wave will fit on here. And so the length of the pipe should be 1/4 of the wavelength that you want to be amplified. So you can say, like, say I want the note, a C note to be played, which is 440 hertz, I think. Then you can calculate based on the speed of sound and that wavelength. You can calculate the based on the frequency 440 hertz and the speed of sound. You could calculate the length of that wave, and then you can say, okay, cut that by a factor of 4, and that's how long my pipe should be. So that's why when you're playing musical instruments, when you press all the buttons or you change the length with a trombone, you're changing the length of the tube so that various different frequencies are the ones that resonate, and then those are the ones that you can hear. So suppose you wanted a frequency that was higher, you'd have to have a longer tube. And another way you could visualize or think of this as there's different harmonics, which means another way, even in the same tube, another way that you could get the same behavior, where you have a node here and an antinode here, is instead of fitting 1/4 of a wavelength, you could come over to here, because here's another antinode. So you could fit 3/4 of a wavelength. And if you fit 3/4 of a wavelength, it's 3 times as much wavelength. So you're going to have 3 times, wait a minute, 3/4 of a wave. So 3 times more frequency. Yeah. So the wavelength here is actually shorter. So you can see the wavelength here, like the length of a quarter wavelength was the whole pipe, and now the length of a quarter wave is much shorter. And so the wavelength got smaller, and so the frequency got higher, because you fit more wavelengths in the same space, so the wavelength must be getting smaller. Anyway, so I'm not going to go through all of them, but you can fit lots and lots, and actually an infinite number of combinations in here. But usually the fundamental one is the first one, and that's the one that's heard the most when you play an instrument. Okay, if you have an open pipe at both ends, an example of this kind of instrument is an oboe, then you need, let me draw the little wave again. You need, let me go through the middle here, finish it off. You need to have an opening with on both ends with a maximum oscillation, so maybe like right here and right here. Those are the two endings that you could have, and that's going to be from here to here is 1/2 a wavelength. And that represents the fundamental on the open tube. So it's 1/2 of a wavelength. So again, you can relate the frequency to the wavelength to the velocity, and then you can figure out exactly what note is going to be amplified based on the length of your tube. And then when you're playing your instrument, you change the length of your tube, and then you get different sounds that are amplified. And then this is the second one, third one, fourth one, and they're called overtones. I'm not going to quiz you guys on the actual musical terms. I just want you to know this general idea and be able to calculate, like, what frequency is going to be amplified if my tube is such and such length, or whatever. And so to do these, you want to be able to draw the picture of the tube with open or closed ends, and then draw in the actual wave inside the tube. Second thing here is a string. A string is fixed on both ends, so it behaves in the same way as a pipe would if it was closed on both ends. And so you have to have a node on both ends, so you can fit here. This is a half a, again, like if that's a whole wave, then what we have here is a half a wave. Here we have a full wavelength, then we have 1.5, 2, etc., etc. So the frequency here on a string just goes up by a factor 1, 2, 3, 4, 5. And this is exactly what you saw in the video. The first three were this one, and this one, with the different amounts of motion in there. So the fundamental frequency is the first one, and then the different harmonics are each increment after that. Okay, the last thing in this chapter is on sound quality and distortion. So a perfect, like a pure note, is going to be a perfect sine wave oscillation of the air particles and the pressure. So perfectly smooth is an ideal world, but actually the human ear, maybe we're conditioned by the different music that we hear, or maybe we're naturally this way. I don't know. But real sound waves are a combination of lots and lots of actual sounds coming in, and so they get distorted. So this orange line you have right here would be a pure sine wave, but then the green one is a little bit distorted. It's not, I mean, it still has the general pattern. It's going up and down, so there's an oscillation and there's a certain frequency there, but there's these kind of overtones in there that you hear, and it just doesn't sound quite the same. And then the blue one, you can see it's very kind of up and down, up and down, up and down a lot. And so the way you get those distortions is by combining multiple other sound waves all at different frequencies. So the net effect looks like this, but there's a lot of other frequencies going on. And so when the sound wave comes into your ear, it's not just the one membrane or the one little hair that's oscillated that says, okay, I'm hearing an A sharp or whatever. There's a lot of other ones that are also vibrated, maybe not as much amplitude, but they're also vibrated. So you hear all these other sounds at the same time. And I've got some sound clips that will help you see that, although I'm sure all of you have already listened to distortion before. But so here's an original with no distortion. Here's the same one with a little bit of distortion. Medium amount. And heavy distortion. Let me go back to the original just to compare. Okay, so I just want you to kind of hear the differences and think about when you listen to music, are you listening to pure tones? Are you listening to distortion? What sounds better? Obviously, a lot of musicians, they distort their music on purpose. They like how that sounds, or it's part of what they're trying to convey to the audience. And so distortion plays a pretty big role in the overall making of music. Okay, let's recap briefly chapter 15 on sound waves. So sound waves are longitudinal compressions of the air. So the actual air particles are oscillating back and forth. And the way that we hear that is using our ear. The pressure, as they oscillate back and forth, the pressure next to our ear is either higher or lower. And that oscillating pressure is translated into our ear, vibrating hairs, which send signals to our brain. But the sound wave that we actually hear is based on, well, we map it out using a decibel scale, because the range of pressures is over 1,000,000 times from the smallest to the largest. And in order to graph that over a reasonable range, we use a decibel scale. Then we looked at the Doppler effect, which is frequencies in front of a source, a moving source, will hear a higher frequency, and observers behind a moving source will hear a lower frequency. We saw that the source of all sound waves is always something vibrating or oscillating. And lastly, we looked at open and closed pipes and strings as different ways to find resonance to play a certain tone at a larger value. Now, I just realized there's one thing I glossed over that I want to go back to, which is on the decibel scale, not just the relationship between the pressure and the decibel scale, that's a mathematical relationship, but the perception of the sound. So let me zoom back to the decibel scale. I apologize. So when you're talking about how loud something sounds, so this is very subjective, but if you ask someone, okay, which of these two sounds is twice as loud as the other one, something like that, on average, humans perceive a 10 decibel increase as roughly twice as loud. Okay, so that means a 20 decibel increase is twice, in other words, 2 squared, which is 4 times louder. A 30 decibel increase is 2 times 2 times 2, or 2 to the third power, which is going to be 8 times louder. A 50 decibel increase is 2 to the fifth, which is going to be 32 times louder, etc. So a logarithmic scale is also, if you invert that, it's an exponential. So logs and exponents are inverse of each other. So if you create a logarithmic scale, then when you amp up the log side of it, you amp up the sound here exponentially. So you need to memorize. That's why these are blue boxes. You need to memorize these two factors. The mathematical one is that 20 decibels is 10 times more pressure amplitude. And then the conceptual or subjective one is that 10 decibels for the average human is twice as loud. And that pretty much does it for chapter 15. Let me know if you have any questions.